how AI and the generative AI is the revolutionizing disease diagnosis, including rare diseases. I'm Andrea Dobrindt. I'm a data scientist, and I lead the AI ML automation and the generative AI automation at IBM Consulting. So here are my teammates, Summer.
Hello, everyone. My name is Summer Jai, and I'm currently a senior data scientist also from IBM Consulting. I'm based here at New York City office.
Yeah, my name is Theophilos Ijebo, senior data scientist, IBM here in New York.
Thank you. So here is our talk agenda. We will start with the excitement of leveraging AI in medical imaging diagnosis and the associated challenges. And we are going to share our solutions, approaches. And after that, we are going to cover two demos. One is image-to-image generation. The other one is text-to-image generation. And after that, we will share our point of view on the important steps that need to be taken before clinical implementation. And our talk will take about 30 minutes, and then we will have a Q&A session at the end. Okay. So without a doubt, artificial intelligence is the most discussed topic today in medical image area. And AI has the advantage of uncovering disease characteristics that human eyes cannot catch. So this includes different image modalities like CT, MRI, ultrasonography, etc. And the different tasks like tumor detection, segmentation, and the disease prediction. And the new era of AI, combining the generative AI and the traditional AI, have so far demonstrated very promising improvement. So the potential applications are vast. But similar to human learning, deep learning also need to learn from numerous amount of image examples. So medical image analysis also requires medical imaging data set. So that process includes the entirety of a medical imaging life cycle, from image creation to diagnosis to outcome prediction. However, currently, researchers have been described as data starved. Why? So the first obstacle here is the data privacy. And patient-related health information was protected by tight privacy policies. And making a clinical medical image available for research requires regulatory approval. It also limits cross-institution image sharing. So that's why relevant images are usually in high demand and short supply. The second challenge here is image quality. The way each clinic practices is different. The quality of the data generation from different practices can be very different too. And if we can overcome these challenges, the cost saving that AI can bring is very significant. It is estimated that AI applications can cut annual US healthcare costs by $115 billion in 2026. But how can we overcome these barriers? We believe that synthetic image data specifically can be one of the solutions. Synthetic image data is artificially generated image data as opposed to data collected from real events, which mimics real-world patterns to represent high fidelity to reality. You can see the top 5 advantage here of synthetic image data. It protects patient privacy because it reduces the needs of real patient data And the second, it provides large amount of diverse training data that are crucial for building robust and reliable AI models. So the diagnostic model accuracy can get improved with the more synthetically generated training data set. And the synthetic image data can be generated at a lower cost compared to real data. It can reduce the time and the cost of a challenging real-world medical image data. It can reduce the time and the cost of collecting the real data. So this allows us to save time and the money while still being able to train the diagnostic model effectively. So now I'm going to turn the stage to Summer to talk about the technical details and showcase the demo that we prepared for the audience here.
Thank you so much, Andrea. And now moving on. First, I would like to say that, since Andrea mentions lots of benefits and importance of synthetic images and how it came to play for medical diagnosis, we do want to dive deeper into the demos here. So basically, we will introduce the two types of models, and we'll be showing two demos. And since all of those methods are not only applicable to the medical diagnosis area, but are also applicable to other domains as well. So start thinking about your own generative task from today. The first type of model we want to mention is image-to-image model. The second is text-to-image model. Basically, the first one is those generative models that will learn the mapping, use a real image as the input during the training phase, and they will learn the mapping phases during the training process, so to reproduce this new variation as close as the real image and to generate the synthetic data. Some popular models include GAN's models, VAE's model, and diffusion models. Due to the limitation of time today, we won't go into details for the previous two, but diffusion model is probably one of the most popular models going on in all the domains. We'll be covering a demo today for the latent diffusion model, and it's both applicable to 2D and 3D image generation. The second type is the text-to-image models. Basically, it gives you a ChatGPT-like experience. We use both text and image as the input for the training phase, and then we will use the natural language prompt to ask the model to generate one image for us. Pretty easy, right? Some popular models is Stable Diffusion. This one was published by Stability AI. It's completely open source. You can access it via Hugging Face. You can also fine-tune it, and we will be demoing it today. Also, we got DALL-E 3. This one was recently released, I think earlier last month by OpenAI, and is now available in ChatGPT 4. Also, we got Midjourney. This one is mainly for artistic image generation, but we are starting to see its application in other domains as well. So now moving on to the first demo belongs to the image-to-image generation category. Basically, we will be leveraging latent diffusion model to generate 2D chest X-ray images with pleural effusion. We came up with this idea because pleural effusion is one of the most common lung disease, and it's affecting 1.5 million Americans every single year. However, for some downstream tasks like classifications, or if you want to build some diagnosis assistant, it requires a very tedious and tiring image collection process. So that we come up with this solution to use a open source data set. It's called MadMist, and it contains different types of 2D and 3D images, including chest X-ray with pleural effusion. And we use it to train our own latent diffusion model. And afterwards, we actually compare lots of other state-of-the-art models as well, and turns out latent diffusion model was outperform all of it with the lowest validation loss, which was based on MSE. And on the right-hand side, there are some sample images. The first three are like our sample input for the training process. And on the right-hand side are like the sample synthetic image that was being generated. And now we will go to the notebook to show you how we make the whole generation process work. Yeah, let me know if this font size is okay. So basically, first, we want to give credit to the open source framework MONAI we used. For those of you who are not familiar with MONAI, this is a completely open source, free, available collaborative framework that's built specifically for medical imaging. It's built upon PyTorch, and it's giving you lots of because for medical image, one of the difficulties to read the image, since they are of very high resolution, and some of it requires DCOM or some special type of image type that requires lots of different software to use. So this is a really, this software is super helpful. So we want to give credit to it. And then I'm not sure if everybody here is familiar with the latent diffusion model, because before I started this project, I was not at all familiar with it. So I just want to use 1 minute to quickly share with you how it works. And don't worry if you don't follow, because we will be showing this graph for multiple times afterwards. So basically, we got the real image X, and we will put it into an autoencoder to generate its latent representation in this lower dimensional space. And then coming to the diffusion process, basically we are adding random noise to this generated feature, this lower dimensional features, to get ZT, which is the noised feature. And then we will train this, we will put this ZT, this noised feature, as the input for the denoising unit to be trained to iterate for T times, which the unit will learn how to predict and thus to remove the noise in each of the iteration. During which we will also have this conditioning layer, which you will be applying other conditions as well to make sure you are getting the image you want. And afterwards, you will get this reconstructed feature Z, and we will put it back to the pixel space by using the decoder to get the synthetic image. So that's how it worked. Pretty easy, right? So now let's set up the environment, imported lots of functionality from MONAI and also Torch. Then we would like to get all the data ready. We first we got all the image from the MedMist dataset. This is also a publicly available medical image dataset. It contains, you can see different type of data like hand or head CT or breast MRI, different kind of 2D and 3D images. But to work for our end goal, which is for chest X-ray with pleural effusion, we only use this particular type of image here. And we are visualizing it to make sure we are getting the right images. Then we set up our validation data set as well, so that once we get everything ready, we will first define the autoencoder here in the red box, which we've covered before. This autoencoder comes with this KL regularization to make sure it was transformed into this latent representation, while also the distribution is still in accordance with Gaussian distribution. Basically, to do that, we need to initialize this autoencoder KL, and we will specify the perceptual loss, the adversarial loss, and also the optimizer. And then we train this autoencoder. You probably need to change the epoch here based on your computational resource. I was actually training it on my local machine. It was pretty quick, very impressive. But if you have a higher computational resource, probably you should change it to 100 or 200. Yeah, and we can see the result here once everything finished. You can see the reckon loss is decreasing, looks good, and we can visualize all the intermediary images and also what's the latent representation being generated. After that is done, we will move on to the diffusion model, which is the large green box here. To begin with, we want to get all the parts ready. Like the first important component is the diffusion process. Basically, it's here we want to add random noise to the latent variable z. So we add the noise, we will iterate it. And the second component is inside this latent space, we will also want to get the UNet setup ready and also all the schedulers. So here we want to set up the UNet and also getting the scaling factor. This also makes sure the signal to noise ratio doesn't deviate too much from a Gaussian distribution. And we have our scheduler ready. We wrap it up into this inferer, and thus we can start this whole training process. Basically, it works as follows. We use the autoencoder to get the Z, which is the latent representation. We then add noise. You need to fine-tune the timestamps here, and then the model will predict the noise instead of the actual pictures. So yeah, we do so for both to get the training loss and validation loss. After all the epoch finish, we can plot a learning curve to see, okay, the loss is constantly decreasing. And last but not least, we want to bring back to the pixel place so that we can get our synthetic image, which is our end goal, right? So we decode the image, and I want to show you guys how the noise is being removed gradually. So I wrap everything up in this function so it can show you like, and first it was like a random noise, and then the UNet is iterate, so it gradually removes the noise, and then you get this synthetic image. Well, so basically that's it. You can change the function a little bit so that it will only give you the synthetic image instead of all the intermediary steps. But that's how it works. And now I will pass it on to my colleague Sue to talk about the text-to-image generation.
Yeah. Thank you so much for that wonderful presentation. As earlier mentioned, you will agree with me that most of the problem we face in the field of computer vision is lack of is the area of data augmentation and annotation. And in general, many people have faced this issue because of privacy concerns earlier mentioned. So we came up with the idea of, okay, how can we leverage this stable diffusion model or other portrait model, maybe in the Hugging Face or in the stable diffusion as well, so that we can generate more images you can use to train your model. So going with that, we start by, just using the same data set from the main list. We work on the pneumonia, because if you watch very well, most of the people, not just only in America, across the world, there is issue with people suffering from the case of pneumonia over the world, killing large number of people. So what can we do to be able to mitigate this effect? We leverage on this model to be able to do that. And when talking about stable diffusion and text to image, it has two main components, whereby you send your image to the model, encode that image to the latent space. Then you give a text prompt to that image. Then you will not do a kind of a cosine similarity computation, whereby you do the dot product to know how similar the image is. Then you can retrieve that same image from the train model. From here, you can see from here, this is the real image. This one here is the real image we get we use in training our model. Then when we prompt the model, okay, generate image of a pneumonia, which you can also apply to your own personal use case. Maybe you are in advertisement or anything you want to do. You have a cloth or anything, just use it to train your model. Then when you give a test prompt, you will learn from that distribution of that your image or whatever use case you want to work on. Then it can give you that same image back. Then if you check very well, one of the images is the prompt image I gave, which is the first one here. to give me a test prompt to give me an image without pneumonia. Then I feed it back to this pre-trained model I did, the classifier, which is this particular one, to really check if the synthetic image generated is really in the confirmation with what I really want. And the model was able to classify that, yes, it's really a normal image. I also did the same thing for the case of a pneumonia. I give a test prompt, give me an image of a pneumonia image, then I have that. I also check, and I was able to, the model was able to check, give us a case, okay, it's really a pneumonia, just to validate the test synthetic image you are generating, if it's really what the model or the classifier or whatever training you want to do. So going back to the notebook, like I said before, we leverage on the stable diffusion model. At this point, which I've already explained here, that the reason why we need stable diffusion and all of that. Then we install our dependency. For here, I just check this, my GPU, because training in stable diffusion, like with your images, it really takes a lot of times. So you have to know you have the enough capacity and all of that to do that in terms of your device. Then I load it from my drive, where you get your data, you can load it from there. From here, because of the model I'm using, pre-trained model is really from the Hugging Face interface. So you have to ensure that you're able to log into the Hugging Face. Then that's why I did this. Then from here, I set up the parameters like the precision recall and all of that will be able to know the performance of your model. At this point, I load the data set. I load the data set. Then we have a class of a case of a pneumonia and non-pneumonia at this point. You can see from here. Here, we just do some transformation, like in case maybe you flip the image around, like 0 to pneumonia to 0, this kind of stuff, in terms of label images. Here, I define this is the pre-trained model I use from the Hugging Face, already, yeah. Then I define the data set where I'm going to be getting my data set from, which is this particular place. Then this is the name of the model I gave, which is the text to image PyData 2023. So I specify the static parameter I'm going to use. You can really find this in the Hugging Face interface and how you can train your model. One thing you should note here is that when training, you must be able to specify your parameter correctly. Like your image must be 512 by 512. Otherwise, this will fail. Then that was the case of generative image. Then I build a classifier, leverage on the same model. Then from here, we do the image transformation. Then we define the function to compute the metrics. Then we do the training parameter. Here, the training start, we did the training. Then the validation loss, as you can see, it reduced drastically, as well as the training loss. From here, you can see from the graph how the validation and the training loss reduced during the training. Now, look at the confusion metric here. But when you can see fully well that it was able to perform well in terms of generating a pneumonia image. Same with the number, but it misclassified in terms of some number. So, which also subject to further training or image. Then at this point, this is where I write a function to do the generation. So when I say, okay, generate chest X-ray image with pneumonia, then I specify the number you want, 10, 20, 100, or whatever. At this point now, you can get maybe thousands of images of the kind of test you want. Then this is where we get from for the synthetic image. You can see very well that is exactly the same original image. But one thing you should note here is that when giving a test, the prompt here is very important. Sometimes because they are in the same latent space, it can generate the same image for you. So it learns from those parameters and all of that. So that is it. From those synthetic images, we give you the test, like I said before. Thank you so much.
So now you've seen the demos of image-to-image and the text-to-image generation. And here are the pros and the cons of each approach based on our experience. So with the image-to-image model, it's proficient in generating both 2D and 3D images. And we have a more control over the parameter tuning. And the fidelity of the output of the image is relatively higher. And however, the technical expertise around tuning the parameters are required. And the interpretability is a little bit low, meaning that it's hard to explain to non-technical people how to how to generate image based out of image. And with the text to image, it's a required different set of a domain expertise. We need to learn how to best tune a prompt, right? And the legal, ethical concerns come with it. And how to make AI and generative AI more trustworthy is a hot topic right now, an important topic. And specifically, how we make sure the output doesn't have a bias, no toxicity, and no personal information. And then lastly, we cannot use this approach to generate the 3D images yet. Before the synthetic medical image can be used for the development of AI algorithm, certain steps need to be taken. And first is the data preparation, right? We need approval of the use of the medical image due to privacy concerns. And after ethical approval, we need to standardize it, right? The data from different organizations and how to make it standardized and have them share the images. And after that, we want to identify the personal information and go through quality control and have it labeled, right? So then that's the data preparation. The next one is disease diagnosis. That's the end goal of generating this synthetic data, is to create enough training data set that can be used for the diagnostic model, right? To make that model more accurate. And this is a downstream task that we did not cover today. And the last but not least, we need the medical professionals' input. And we need their guidance in this process. Medical expertise will help us to better create the ground truth for the training data set. It also provides the more accurate diagnosis interpretation. So here is the last slide. This summarizes the end-to-end life cycle from image generation to diagnosis and to outcome prediction. And the input can be image or can be a prompt. And it goes through different models to generate the synthetic data, as we demoed. And that synthetic data need to be validated by clinical professionals before they are qualified to be used for the diagnostic model. And to conclude today's talk, the new era of AI, combining traditional AI and generative AI, has shown promising advantages in this research field. And with the current success of AI in image research, we anticipate that it will continue to play a dominant role. And our team is dedicated to making contribution in this exciting field, and we look forward to further the development and the innovation. Thank you very much.